This is a PDP-11 released in 1979. It had full 22-bit addressing for a maximum of up to 4 megabytes of memory, and the Unibus CPU in this thing is the last non-LSI based 11, meaning there's no microprocessors in there. It's all discrete logic and AM2901 based ALUs. This thing is pretty gnarly, and my goal is to turn it into the best PDP-11 on the planet. Now I'm gonna need to do some pretty tricky things in order to get that done. The first is that currently it has 1 megabyte of memory in it, and I need to push it out to 4 megabytes. I have those cards, I just need to get them in there and get them tested. I also have the commercial instruction set boards. These are really rare and really flesh out the 1144. We have to get some pretty big storage going on. I have dual 8-inch floppy drives here, and we're working on a Priam hard drive. But just that alone is not going to be enough to take it to the next level. We need to turn this thing into a supercomputer, and we're going to do that using a floating point systems FPS 100. To be clear, today is absolutely about the Priam hard drive, and we're going to dive into that heavily soon. But first, I have some updates on the floating point system story here. I got in touch with Mr. White, who is the architect of the FPS 100. He got hired by Floating Point Systems, and one of the biggest jobs that he did was actually taking the AP120B array processor architecture and miniaturizing it down into the FPS 100. Oh, first of all, absolutely amazing story. And Mr. White, if you're watching, it was just an absolute pleasure to talk with you on the phone, and I'm sure I'm going to have a million more questions for you because we're making some pretty amazing progress because Mr. White had the full schematic set for the FPS 100. The problem that we have with my FPS 100 is all I have is this front panel and a bunch of cards. I don't have the backplane, and the backplane was a custom wire wrapped thing. And without knowing the pinout of each of the individual cards, I couldn't create a new backplane. But now that we have a full schematic set, I know the pinout of all of the cards, which means that we can start making a new backplane from scratch, building a new FPS 100 to plug our card set into, and then we can get that array processor plugged into this PDP-11, and we can build ourselves a supercomputer. Man, I am like crazy excited about the FPS 100. This is really, really cool. However, it doesn't mean anything if we don't have any kind of storage on this machine, and we've kind of been through the ringer trying to get a hard drive working on this. And this is the drive that we're going to use. It's a Priam. I think it's technically supposed to be pronounced Priam, but I'm stuck in my ways. So I'm probably going to keep calling it Priam, and the people in the comments are just going to go nuts. But Priam made 3 different versions of this drive. They made a 3350, a 6650, and a 15450. These have 33 megabytes, 66 megabytes, and 160 megabytes respectively. This is the 15450, which means it's 160 megabytes spread across 2 platters in the HDA here, and it uses MFM encoding and has an SMD interface, which means that we can interface this to the PDP-11 using this card right here. This is an Emulex SC121. This is a Unibus based SMD interface. So we have everything we need to get a hard drive going on that machine, except for the fact that this doesn't work at the moment. We've got a couple of problems going on here. In the previous episode, I made a big glaring mistake that a lot of you guys caught. I got my data sheets all mixed up in my brain, and I thought an LS244 and an LS245 were interchangeable. They absolutely are not. So I've got the appropriate chip here for that, so we're going to fix that. And there was a bunch of components on the analog board here that had been damaged. Something had fallen into this board and destroyed a ton of resistor packs and transistors and messed up a bunch of other stuff. So we went through and tried to clean all that up and fix it as best as we could, and we made really good progress, except I didn't have replacement resistor packs because there's this like weird custom thing that's going on with really strange layouts of the resistors. So instead I made these like abomination freeform resistor things that plug in, and I'm losing sleep over these things. They are awful. So before we do anything else today, what we're gonna do is we're gonna fix these things. I'm gonna cut up some little PCBs, solder some proper resistors in place, so that way it doesn't look like some eldritch horror going on my analog board here. And then once we get that taken care of, we can start digging into why it doesn't spin up. Whenever we put power into this thing, the discs spin maybe like 1/8 of a turn or 1/10 of a turn, and then nothing. So we're gonna have to dig in deeper on that as well. But first things first, man, let's fix these resistor packs. Let's start easy. I'll pop the incorrect LS245 out and slot in the proper LS244. Well, that's all the easy stuff done. Now for the hard stuff. I'll fire up the mill and get it cutting out some small PCBs. These are going to be my solution to the monstrosities that I built before. Plus, it's just so mesmerizing to watch the mill churn away, creating new PCBs from scratch. Although the kitty didn't think so, Sue here decided he'd go hang out somewhere else. Back to the PCBs, they're shaping up really nicely. Time to change tools and jump over to drilling the through holes. After a final tool change to cut them out, I now have a bunch of somewhat large resistor packs that'll work perfectly. In total, there are 13 resistor packs that I need to change out. Some are simple and some are fantastically complex. So let's get to work. First, let's remove the 10 screws that hold the interface and analog boards in place. Then I need to remove the grounding strap that goes from the analog board to the voice coil. And finally, I need to disconnect all the connectors for the voice coil and heads. With everything disconnected, I can pull the interface board out, followed by the analog board itself. Next is a lot of desoldering. I need to remove all the old resistor towers I built. Fortunately, the solder is fresh and it desolders moderately easily. Then with the help of a pick and a little gentle rocking, the last vestiges of solder in the through holes break loose and I can pull the resistors free and clear. Once everything has been removed, I can start populating the resistor PCBs. I'm still using through-hole resistors here because I don't have steady enough hands or the machining capability to do surface mount stuff. I'll slot each resistor in place, solder it down, then fold the legs through and solder them in nice and tight. These will be the legs that go through to the main PCB. All in all, it's quite a bit larger, but so much cleaner. And this was the easy one. This is a massive improvement. This is way, way better. I think it looks absolutely stunning. I love the cityscape appearance that's going on here. It's like Mega City 1. There should be dudes on motorcycles driving around. I am the law, right? Like it looks really good. I am embarrassed about the abominations that I had built before, but this came out looking fantastic. They are unfortunately a little too tall, I think. You can see they stick up quite tall, particularly this one all the way back here in the back. But honestly, I think this is gonna be all right. I just have to be cognizant of where I put it in the rack to make sure that there's enough space above it. But it's not going in the rack until it works, and it's like, it still doesn't work. Like this did not fix our fault, where when we put power into it, we get just a little bit of a rotation and then nothing else happens. But you guys left some pretty awesome comments in the previous episode. I previously did not understand that there was a connection between these control boards on top and the spindle motor board on the bottom. I thought they were completely separated, but it turns out that spindle control board receives an on-off signal from the analog board up here. So I think that's our first place to start checking, because that drive board may be totally fine and the fault may be up here, which would not be surprising given how much damage had happened up here. I've got the schematics open on my laptop here, and we can see there's a signal here called off, and it looks like this is kind of an open collector thing because we got to pull up to 5 volts with a 1K. We go through a couple of inverters, and that feeds off into multiple different directions. One of those directions is into this IC right here, which is a 74S188. This, I believe, is a little PROM, a little programmable read-only memory. And this is actually, I think, being used to generate the three-phase signal that is going to be used to spin the drive. So where does this off signal come from? Well, we can see here it says it comes from connector J2-4. And if we go to page 17 here, we can see that J2 pin 4 actually connects up to J4 pin 4 on the interface board here. And that signal actually just passes straight through to J5 pin 42, which is this big connector here. So it's just a straight connection up to this connector, and then it goes into our previously heavily damaged analog board, which is a bit of an issue. So if we follow that signal over to page 11, we can see on the right here we've got our on-off signal coming in on pin 42. And if we follow that all the way around, it looks like it goes to pin 36 of the 8741. Now, I don't have an 8741 on this board. This is a revision change between the board that I actually have and these schematics. But I do have an 8035, and I've beeped it out, and it does go to the exact same pin on the 8035. So that is our on-off signal. I think that's where we need to start. I believe this is going to be an active high signal, at least in the schematics. They don't draw it with a bar over it. So we're hoping to see it go high, I guess. Let's flip the switch and find out. It started low, and then it popped up to high. That's potentially good news. Next up, we're going to check the address inputs into the little PROM right here that should be generating the three-phase signal that's actually spinning this thing. And there's 5 address inputs on this PROM chip, and I've only got 4 channels on the scope, so I've got 4 of those hooked up. But these should be the 4 addresses that are not from the on-off signal. On the scope here, I've got all 4 signals set up on a 1/2 volt spread, so they should, you know, if they're doing something, we should see them do something. Here, let's go ahead and flip the switch. Well, we saw a little something there, and then it came to a stop. I wonder if I spin this. Oh, yeah. Wow, look at that. If I spin the spindle by hand, we can see the addresses moving around. It's really fascinating. I love that. Okay, so our problem lies elsewhere. This board mercifully matches the schematic much closer than the analog board up top, and there are 2 transistors per phase that drive the motor here. These 2N6059s, these big boys here, these are NPNs, and then we have tip 145s here. These are PNPs, and these two kind of work in conjunction, it looks like, to provide the 3 phases out to the motor. But the input to these 6059s has these massive 750 ohm 3 watt pull-up resistors to plus 24 volts. So I've got the probes hooked up to what I believe is going to essentially be the base input of these 3 NPNs here. I've changed the scale on the scope here to 5 volts per division, and we're only looking at 3 signals because we're just trying to look at 3 phases here. So let's go ahead and flip the power switch on. 2 of them have gone high, 1 of them stays low. If I rotate the spindle, nothing changes. So it seems to be kind of stuck in that state. That's interesting. I've moved the probes over to these 1.5K 1 watt resistors. These are going to be for the PNPs that are these tip 145s here. Scope is still set up exactly the same. Let's go ahead and flip the switch, see what happens. Oh, interestingly, all 3 went high. Okay. Oh, if I spin the spindle now, I can actually see differences happening. They're offset to an interesting level, but looks like those are trying to go through the motions. All right, I've been probing around on this thing for a while, and things don't look right, but they also don't look wrong, which is like a weird place to be in. But this might be a power sequencing thing. The plus 12, plus 5, and minus 5 volt rails all come up pretty much simultaneously, but the plus 24 volt, meanwhile, is a little slow to boot up. So check this out. If I put the scope here into single shot mode and we flip the power switch on, it tried to start. We got a single shot here, and this is pretty telling. The blue trace is the plus 5 volt rail, and we can see it goes from 0 to 5 volts pretty cleanly right here. The purple trace here is the plus 24 volt rail, and I'm DC coupling this, so it's like way off the bottom. But you can see that there is 1, 2 and change divisions between the two, and I am sampling at 500 milliseconds per division. So that's like 1.2 seconds of a time difference between the 5-volt rail coming up and the 24-volt rail coming up. If it's a power sequencing issue, I wonder if it's giving up before the 24-volt rail comes up fully. So let's give this thing a bit of a spin by hand, and then we'll flip the switch and see what happens. I'm skeptical this will actually do anything, but let's give it a bit of a spin. It is pretty easy to spin, so I don't think it's bad bearings. Okay, and then we'll flip the switch. Nope. All right, let's fix this power sequencing problem. First things first, let's get the analog PCB out of the way. And I'm going to solve this problem using a pair of relays. All I have are these 12-volt automotive relays, so what I'll do is put the coils in series on the 24-volt rail. The 24-volt supply is the slowest to come up, so it makes sense to have it controlling the relays. Then I'll use the relay contacts to gate the plus 24-volt and plus 5-volt going to the hard drive. The negative 5 and negative 12-volt rails will come up first as they power up immediately. To get these relays mounted in place, I'll use a piece of scrap steel I had laying around. After marking out the measurements I need, I'll take it over to the metal shear and give it a solid whack, slicing it to size. Then I'll move it up to the brake, get it in place, and put a nice 90-degree bend into it. After drilling a couple of holes, I'll mount it to the plus 5-volt supply using the original mounting holes on it. Finally, I'll start cutting, crimping, and connecting all the wiring to get it to work. It's a little tedious, but the results came out nice and clean, and our power should sequence up perfectly every time now. I'm pretty sure it's okay to bring your bias rails up first. I was looking through some data sheets for like 4116s, and they say to bring your negative rails up first. So, I don't know, let's flip the switch. I don't think it's gonna do anything crazy, but you know, who knows? So here goes nothing. Nope, exact same thing. Well, all right, so we'll just keep smashing small problems and maybe eventually it'll spin. All right, I'm gonna give jump starting it a shot here just because it's the end of the day and I'm kind of running out of ideas. So I will flip the switch, then give it a spin, and we'll see if that does anything. All right, so flipping the switch now, giving it a spin. Negative. All right, let's give that one more try here. Oh, there it goes. It's spinning up. That's insane. Things kicked into high gear here and footage got a little sparse. While it was spun up, I wanted to check a couple of things. This is the output from the driver transistors to the 3-phase motor. And while it looks a little messy, all 3 phases are present and accounted for. I did the same for the base input to the driver transistors, and they all look clean too. Then I spun it down and wanted to check the switch mode circuit path on startup. As it spins up, you can see the pulses getting tighter and tighter. The yellow trace is hooked up to R61. The green trace is the output from the LM339. The blue trace is the pin 4 output of the LS123. And the red trace is the pin 12 inverted output from the LS06. As it spins up, we see sharp pulses on the green trace that trigger the LS123. There's a double inversion happening, and it appears our 2 output traces match, which is good, but even though it's a bit hard to see here, I'm slightly worried about the duration of the LS123 output pulse. Looking at the datasheet, let's do a bit of math to figure out how long that pulse should be. The equation is TW equals K times RT times C external times 1 plus 0.7 over RT. K is a constant, which is 0.28. TW is the resistance, and it's a 10K ohm resistor, so 10,000. CEXT is the capacitor, which is 4,700 picofarad. Put it all together, and we get 13,160,921 nanoseconds, which I think is like 13 milliseconds. Looking back at the scope trace, we're not seeing that at all. So maybe the internal timing circuit of the LS123 is misbehaving? To swap the LS123, I'll disconnect the spindle motor plug and then disconnect the power plug in. The board is held in place with 4 screws. I'll remove the 2 on the bottom first, then while supporting the whole board, remove the 2 on top next. Once it's free, I'll pull it loose. I still need to get the PCB free from the metal mount though. That's held in place with 3 screws and 2 plastic posts. With all 3 screws removed, it pulls free nice and easy. Then I'll do a bit of desoldering, putting that Radio Shack desoldering iron to work, a little prying with the pick, and the old IC pops right out nice and clean. Then solder in a socket for the new IC, and finally pop in a new LS123. LS123 has been replaced. Did that fix the problem? I'm hopeful, but skeptical. So let's flip the switch. Nope. Oh man. Exact same problem. That was not it. Oh, all right. Well, it wouldn't be an Usagi video otherwise. Okay, so the LS123 was not our problem, and hindsight being 2020, I went back and double checked the datasheet, and it turns out that I'm just really bad at reading instructions. Looking back at the formula in the datasheet here, again, it's TW equals K times RT times CEXT times 1 plus 0.7 over RT. K is a constant, which is 0.28. CEXT is the external capacitor, which is 4700 picofarad, and TW is the resistance. But crucially, if you look right here, it says RT is in kilo ohms. I was using ohms for my calculation, which meant I was putting 10,000 into the equation, and instead I should have just been putting 10 into the equation. That's gonna make a massive difference. If I put all the correct values in, we get 14,081 nanoseconds, which is like 14 microseconds and exactly what we were seeing on the scope. So the LS123 was never the problem, and if we check the signal coming on IS, that's the input to the whole chain, and I can follow that entire chain beginning to end all the way across this entire switch mode here, and everything looks fine. So didn't need to replace the LS123, so that's completely on me. But where do we go from here? Well, looking through the manual again, I think the start-stop signal, the on-off signal coming from the CPU, is actually inverse of what it should be. It should be low in order for the motor to start spinning up. And when we looked at it earlier, it started low and then went high. So I think the power board is being told to shut off by the CPU. Okay, it's definitely related to the on-off signal from the analog board. It is preventing this thing from spinning up. As far as I can tell, this driver board is actually working, and I think I can prove that here. The on-off signal comes in to pin 1 on 2F, so we've got that on the scope right now. If I go ahead and I flip the power switch on, we can see that that signal goes up to 5 volts, and we don't spin up. Now that signal comes out of pin 2 of 2F, goes into pin 3 of 2F, and then comes out of pin 4 of 2F. And this is an open collector inverter, so I can actually pull pin 4 low, and I shouldn't damage anything. So I've got a little 100 ohm resistor here hooked up to pin 4, and check this out. If I ground this out, the motor starts spinning. And I let go, and then the motor, stops spinning. So the driver circuitry is totally fine. It wants to spin up and get to speed, but the analog board is telling it no for some reason. Okay, I'm starting to understand a little more here. The yellow signal on the bottom here is our 80% speed signal. The green signal here is our on-off signal coming from the CPU on the analog board. Then the red and blue signals up here, and these are sensor feedback. And I actually have the thing on right now, and if I give this spindle a bit of a spin, you can see those two signals kind of wibble wobble a bit around. So our sensor feedback is working correctly. But if we look at the green signal here, it's currently sitting very high. I've got it right up at 5 volts, which means that the whole thing is shut down. Now here's the interesting part. Let's turn the system off. We can see all the signals go low here. I'll do a single shot, and we'll turn the spindle on here. Our 80% speed signal here creates a pulse right off the bat before it resets. That's just power on reset stuff. And we can see that our on-off signal stays low for a good long while. Then it goes high for a short bit, it comes low again, and then it goes high and everything stays off. During this time, we don't get enough spindle rotation for either of these two to actually do anything. However, if the drive is spinning up while this on-off signal is low, as these create feedback, our 80% speed signal will create blips. And if we get a blip right in this short window right here, the drive will actually spin up. So we'll go single shot here. I'll give the spindle a bit of a twist by hand. We didn't get it that time, but you can see we did get a little bit of feedback here. It just didn't line up perfectly with this window. So let's try it again here. Do a single. There we go. Check it out. Right in that tight window, we got a little blip, and then the whole thing is now starting to spin up. If I click this over to run, you can see that our enable signal is constantly low. The drive is spinning up and getting faster and faster, and the 80% speed signal here is blipping, telling the CPU that yes, there is feedback coming from the spindle. And then look at that, it went high. It's at full speed now, and the CPU will seek the heads. So that is our problem, is that window in which we can get a little blip on our 80% speed here is so narrow that the CPU thinks that it's not seeing any feedback from the motor. Except the real problem here is that I'm a big dum-dum. I've made some pretty colossal mistakes.
You don't say!
I've had my nose buried so deep in the schematics that I didn't stop to look for other documentation, and it turns out that there's a really nice manual out there called the Field Service Manual. It actually has a full flow diagram for how this thing powers up. And if we look at this diagram, we can see that there is a short 40 millisecond window where it tries to detect if the drive is already spinning. And if it is, it continues on with sequencing up. So this is what is happening whenever I spin the spindle by hand and that pulse lands within that 40 millisecond window. However, if that pulse doesn't land within that 40 millisecond window, the power up sequence goes into the idle state, and then from there it goes into a command detection state. And from here, you're supposed to send it a sequence up command that will then send it into the sequence up state where it will spin up. So this thing is actually waiting on a signal from the host machine. And we can confirm this by just reading a simple little passage. Read the manual. That's the moral of this story. Read the manual. So it says, if the drive has an SMD interface, apply DC power, select the drive, then bring pick and hold to ground. So awesome. We figured it out. All I gotta do is plug a cable into this, bring pick and hold to ground, except this is not the SMD interface. This is the Priam interface. I was so obsessed with all of the damage on the analog board that I never looked over to the right and parsed what I was seeing over here, because I don't have a controller card for this. So even if this drive is 100% working, and I think it's pretty close to that, I don't have a machine in this room that can use it. I certainly can't plug it into the PDP-11 I don't know what to do. This is, oh man, I have been striking out over and over and over again trying to get a hard drive up and going for this PDP-11 and I got up to the plate and I just struck out completely again. So we're in a bit of a pickle here. I have a ton of stuff and none of it works with each other. For drives, I have this Priam 15450. I have a spare CDC 9427 Hawk, a spare CDC 9410 Finch, and the Fujitsu M2351 Eagle. For controller cards, I have the KDA50 SDI controller, have the Emulex SC121 SMD controller, and a USDC 1158 SCSI controller. None of those work. Like, I can't use a single one of those drives with any of those controller cards. So, like what do we do? Like, where do we go from here? I don't know, man. I'm pretty invested in this Priam drive. I would really like to see this plugged into the 1144. I think it's the perfect option for what we've got going on. But in its current state, I can't use it. So there's two paths forward here for this drive. I believe there was one single Unibus controller card made that could work with the Priam interface, and I think that's a USDC 1151. I don't have one of those, and Googling, you can find absolutely no information on it. The other path is, let's remove this Priam interface card and build an SMD interface card. We have the full schematics for what that SMD interface card should look like. So there's nothing stopping me from laying all the components out in KiCad and spinning up a new board. All of the ICs on here are pretty generic ICs, and I can still find them, except for one. There's a little ROM on the SMD interface board, and while the ROM itself is generic and I can find that, the code in it is not. Without that code in the ROM, we could build a new SMD interface board and it would still never work. So this is me putting out the call. I need help. If you have a Priam 15450 with the SMD interface card on it, it would absolutely save my life if you could pull the ROM off of it and rip the code off of it and upload that somewhere and send it to me. Because if we have that code, then we can build an SMD interface board for this, get it plugged in, get that plugged into the 1144, and then find out what else is broken. But it'll at least get us pointed in the right direction. So, man, what a weird episode this was. Like a massive amount of work only to realize that we can't use the final product. But who knows, maybe somebody out there is going to save the whole project. So I hope that person is you, and I want to thank all of you for watching, and I hope to see you in the next episode.